Friends, welcome once again. Now friends, in this video I will show you the proof of Euler's homogeneous functions. Euler's, and in short we call it as Euler's theorem. Function, so let us consider function f of x comma y, function of x and y. F of it is of the type a0 x raised to n plus a1 x raised to n minus 1 into y plus a2 x raised to n minus 2 into y square plus a n into y raised to n. So this type of functions are called as a homogeneous functions. Why the word homogeneous? The word homogeneous is about the degree. You can see that if we see the every term of this function, then it is a power of x raised to n here. And here in the second term, if we calculate the indices or powers of these two terms, n raised to x raised to n minus 1 and this y raised to 1, then addition of these two will we get n. Secondly, here in this third term, if we calculate the powers, addition of these two powers, we get n. In the other word, every term is of the same degree. Degree of x raised to n minus 2 and degree of y is 2. So addition of these two is we get n. The degree of every term is n, and therefore in this sense we called it as it is a homogeneous function. Homogeneous function. So what is a homogeneous function? Homogeneous function for the function of two variable is that degree of each term is same. When the degree of each term is same, we call it as a homogeneous function. We can also write it as, if we take x raised to n common, then you can see that we have x raised to n into a0 plus a1 into y divided by x, y divided by x plus a2 into y divided by x whole square plus an into y divided by x whole raised to n. Means we write this in another form as x raised to n f of y divided by x. So this is the treatment of this function, and our another representation of the function of n degree n. For example, if we consider z is equal to x raised to n into sine of y divided by x. So it is a function of degree n. Whereas if we consider f of x comma y equal to under root of x plus under root of y divided by x plus y, then it is not easy to recognize at the first instance how to find the degree of this function. Then by treating in the other manner, here in another representation of f of x, we can easily find the degree of this polynomial. So we take x under root x common from the numerator, and we get 1 plus under root of y divided by x, whereas in the denominator we take x common and 1 plus y divided by x. Here this root x and divided by x, we can write it as x raised to minus 1 by 2, and the other term is it as 1 divided by under root of y divided by x divided by 1 plus y divided by x. So here you can find that or easily we can see that the degree of this polynomial is a minus 1 by 2. So in this manner we can calculate the degree of the polynomial. Now let us write my function is z equal to x raised to n f of y divided by x. This is my function, and this is a polynomial of degree n. Differentiating this with respective to x partially, we get del z by del x equal to del z by del x. Now you can see that this is my first function and this is a second function. Now we apply the product rule to differentiate this. Derivative of the first function with respective to x is n into x raised to n minus 1. Second term as it is f of y divided by x plus x raised to n into derivative of f is f dash y divided by x into, by chain rule, derivative of y divided by x, y is constant as it is, into derivative of 1 divided by x, that is minus 1 divided by x square, equal to n into x raised to n minus 1 f of y divided by x minus x raised to n minus 2, this x raised to n and divide by x square, that is x raised to n minus 2 y into f dash of y divided by x. Now if we multiply this by x, x into del z by del x, delta z by delta x. After multiplication, the first term will be n into x raised to n f of y divided by x minus we are multiplying by x, so this power will be reduced and will be increased by 1 and it will be n minus 1 y into f dash of y divided by x. Now differentiating partially with respect to y equal to, x is constant when we differentiate this with respect to y, x is constant. So first term will remain as it is, and derivative of f, that is f dash of y divided by x into derivative of this y divided by x, 1 by x is constant here and derivative of y is 1. So this will be x raised to n minus 1 f dash of y divided by x. Now multiply this by y into del z by del y equal to x in x raised to n minus 1 into y into f dash of y divided by x. This is suppose equation number 1, this is suppose equation number 2. Now x into delta z by delta x plus y into delta z by delta y equal to addition of these two. I will write firstly whole terms, n into x raised to n into f of y divided by x minus x raised to n minus 1 y f dash of y divided by x plus x raised to n minus 1 y f dash of y divided by x. So you can see that this term will get cancelled, and we have now x raised to n into f of y divided by x is nothing but a z. So friend, we get a beautiful result, that is x into delta z by delta x plus y into delta z by delta y equal to n into z. So this simple result is known as a Euler's theorem. Euler's theorem of homogeneous function. So what is a Euler's theorem? When function there is a function of nth degree and derivative of this, if we then x into delta z by delta x plus y into delta z by delta y equal to n into z. This is known as a Euler's theorem. Now what happens if we differentiate this term further? If we differentiate once again this